Hello everyone, my name is Amir and today I'm going to talk about ergonomically intelligent physical human robot interaction. One of the concerning issues in industries and other workplaces is the musculoskeletal disorders. They are the injuries of muscles, nerves, tendons, and joints that are caused or made worse by the working environments. They are the second largest source of disabilities worldwide, and awkward postures are the main contributors to those disorders. The issue is also very concerning with the recent trend of physical HRI, where the robot can cause injuries to the human during a collaborative task. Teleoperation, which is an application of physical HRI, can be a solution for some high-risk tasks. It is because in teleoperation, you can design the remote workstation ergonomically. However, there is a still high rate of injuries among human teleoperators. To address this concerning issue, we propose ergonomically intelligent physical HRI that includes posture estimation, ergonomic risk assessment, and postural optimization and correction. We also developed a specific framework for ergonomically intelligent teleoperation, which includes the same parts but tailored for teleoperation. In this paper, we start with the posture estimation. Current approaches for posture estimation are prone to occlusion in teleoperation and physical HRI. This is because of the proximity of the human and the robot. For example, you see in these figures that even the gold standard motion capture fails in finding the correct posture of the wrist. Also, all current approaches need extra sensors and expensive setup. Looking at the physical interaction between the human and the robot at the interaction point, we said why not just use the sensor we already have in all of these scenarios? I mean the robot itself. And we proposed a low-cost and occlusion-free idea to estimate the posture solely from the knowing the trajectory of the interacting robot. In the posture estimation problem, we have the observations of the robot trajectory and the kinematic model of the human, and we want to estimate the human joint angles and angular velocities. We know that the observation is a function of joint states or kinematics of human and segment lenses, and we assume that we estimate the lenses independently. We also propose a method to estimate the segment lenses just using the robot, which can be found in our other papers. Now we can write the posture estimation as an optimization. The objective function minimizes the deviation of the hand pose of the solution from the observed ones, and the deviation of the posture at each time from the updated previous posture. However, the problem here includes many sources of uncertainties. So we model the problem as a partially observable dynamic system, and we use a particle filter to solve it and estimate the posture. We conducted a human subject study with 8 subjects and compared our approach with the posture from gold standard motion capture. As we said, mocap postures are not ground truth, so we overlaid them both on a human skeleton to be able to compare them qualitatively. The green skeleton is the posture from motion capture, and the red one is from our approach. Statistical analysis shows that our method has the median deviation of 5 degrees from the motion capture. Now let's move to the risk assessment part of our framework. To assess the risk of injuries, we use RULA, which is a common risk assessment method in ergonomics. The input to RULA is mainly human posture, which makes it a good option for our scenarios. Each part of the posture is analyzed and gets a score. Then the scores go through some tables, and the final risk score is reported as the numbers from 1 to 7. Then there is an interpretation available for each score. Based on the goal that we had to use our posture estimation approach in ergonomic risk assessment, we use RULA on the top of the postures from our approach and compare the result with the postures from motion capture. Here you can see the result for each task and subject using our approach, which are the green triangles, and using motion capture postures, which are the purple circles. Each color bar is also an interpretation of RULA. Our approach is 84% accurate in RULA interpretation and 65% in exact RULA score comparison. Also, we have to mention that the difference was 1 at the maximum. Now let's move to the postural optimization. We can model the postural optimization as this formulation, in which we want to find the most comfortable posture that results the same pose of the hand as the one that we observe. There are 2 main points here to focus. The first one is a mathematical model for ergonomics and human comfort, and the second one is task parameters. We address these in the following. As I mentioned before, RULA as a risk assessment model has discrete output, and it's not differentiable. Instead, we learned a neural network model based on RULA. We called it differentiable RULA or DULA, which is continuous and differentiable. We used a 5-layer fully connected neural network to learn it, and it has test accuracy of 99.7%. You can also see the confusion matrix for different risk scores. Now we can use this model in a gradient-based postural optimization. To have a general framework for each type of the task requirements in physical HRI and teleoperation, it categorizes these tasks into these categories. The details of each task is available in the paper. Here you see the example of postural optimization in teleoperation. In the goal constraint task, such as pick and place objects, the follower robot can take any path to reach the goal post. In its corresponding online postural optimization, the intelligent system calculates the instantaneous optimal posture and suggests it to the human. In the path constraints tasks, such as turning a valve, the follower robot should follow a certain geometric path to do the task. It means that the human can use a clutch to disengage the remote control and move to a better posture, then resume the task. We called it posture optimization through the interface reconfiguration. The intelligent system calculates the optimal resume posture and suggests it to the human. The human also can do a task once and then start the next round of the task from a better posture. In this category called initial posture correction, the intelligent system finds the optimal initial posture from which the same task can be achieved completely. The third category of teleoperation task is called trajectory constraint task. It can also use the initial posture correction as the postural optimization method. In these type of tasks, such as teleoperated welding, the follower robot should follow a certain path and velocity profile to complete the task and cannot stop in the middle. We solved the above optimizations using both gradient-based, using DULA, and gradient-free optimization using generic RULA. To evaluate our partial optimization approach, we developed a physical HRI and teleoperation simulator in ROS that includes robots and a human doing the task. The postural optimization calculates the optimal posture and suggests it to the human simulator. Human simulator applies those postural corrections in a probabilistic way by moving toward the suggested postures while continuing the task. The human model does it using an optimization-based replanning algorithm. Here you see the risk scores during a simple goal-based teleoperation task using both gradient-free and gradient-based postural optimization. The orange lines show the risk scores for the task without optimization. The green lines show the risk scores for suggested optimal postures. And the blue lines show the risk scores for the corrected postures. You can see that the corrected postures from the gradient-based approach using DULA have lower risk scores, and the suggested optimal postures are also smoother. In the bottom figure, we did the same similar scenarios multiple times, and you can see that the same behavior from the previous result is shown here too. In summary, we are targeting the problem of prevalent musculoskeletal disorders in physical HRI and teleoperation by proposing a systematic, autonomous, and intelligent framework that includes novel approaches for posture estimation, ergonomic assessment, and postural optimization and correction. More specifically, we introduced a probabilistic approach that estimates 3D human posture solely from the trajectory of the interacting robot. We also learned the first differentiable and continuous ergonomic model with 99.7% accuracy, which is more realistic than current approximation of the human comfort in the literature. And we use it in a gradient-based postural optimization and showed that it performs better than gradient-free approach. So far, we have taken the initial steps towards the bigger framework, and we are planning to extend each part of the framework to include better methods and more sophisticated human subject studies in different types of physical HRI applications. For example, we are currently working on combining our posture estimation approach with 2D postures from OpenPost to recover occlusion robust 3D postures. Thank you very much for your time, and I'm here to answer your questions.